It's my pleasure to introduce to you Julius Muschaweck. Julius has been working on optical design for illumination, I believe, for over 30 years. He works as an independent consultant, providing illumination optic solutions to industry, but he's also an excellent teacher on illumination optics, and he's familiar also with a lot of publications, and he also has some excellent books I would really advise you to read. So Julius, please feel free to take the floor for your presentation on the case for angular extent X.
Thank you for the kind introduction, Lynn. And can you see my screen?
I can see your screen perfectly.
Okay. So my friend and co-author Henning and I, we would like to take this opportunity to make the case for a new quantity, which we would like to call angular extent, and give the symbol X. So your first question might be, is this really necessary? I mean, we already have a few, right? So this is the Wikipedia list of physical quantities, and it's endless, and it's only a small fraction of it. So is that really something we need to do? So what would make a good quantity? And I'm sure that all of you recognize that this is just kinetic energy in the very usual way. There would also be a similar but different quantity, which is just mass squared times velocity to the third over 3. And then, this is all well known. This is, I would be surprised if any of you would recognize this quantity over here, because this one on the left, of course, participates in energy conservation. Kinetic energy and potential energy and thermal energy and whatever energy together is always a constant, one of the very fundamental laws of nature. Here on the right side, I would not know of any law of nature where this quantity participates. So this is why this is popular and well known, and this is, no, we're not going to use that. So what makes a good quantity is that, first of all, it shortens lengthy expressions. Of course, you could just replace kinetic energy here with this quantity, and then everything would algebraically be the same, but it would be more difficult to understand. And the second thing is that it must feature prominently in laws of nature, and in order to make it recognizable and usable, it should have an intuitive name. And kinetic energy serves it very well. I think it's been since about 150 or 170 years since Lord Kelvin coined that term. So it's in good use since then. And it needs a unique descriptive symbol. And again, E for energy and kin for kinetic is doing it right, just right. So here in non-imaging optics, we are very much concerned about Étendue. So what about Étendue? So for those of you who are not too familiar with it, Étendue is something like the size, the extent of this beam of light. And the idea is, in this collimating example, light would start from a small area, like this LED or whatever this might be, going into a large angle to the next optical element, and then be collimated into a large cross-section area and into a small angle. And since it's like small area plus large angle becomes a large area plus small angle, it would be an obvious choice to try to multiply it and say that Étendue is area times solid angle. And we have all heard about Étendue conservation. So is this the quantity that is constant and conserved? And the answer is no.
And this is the moment to jump in, because Julius asked me to do so. I want to emphasize that this is a, say, oversimplified picture, and assumes that all the beams on the right are telecentric. So each pixel in the green exit pupil would see the same beam or the same cone. And then the formula is okay. In other cases, it is not.
Mm. But isn't it also just like a paraxial approximation?
Yeah, I think in the paraxial case, this is always true, but in this case, only for telecentric beams.
More or less. Okay. So I'm giving the talk, but it's really based on ideas that Henning and I developed over the years together. They're basically writing our books. So this is one attempt at Étendue, but it turns out that we neglect one important thing, which I would like to call the cosine factor. So with this situation, there's a ray with something like a small, thin, very thin light tube around it. So it's coming from a small area, going into a small solid angle. And as is immediately clear, when you look back along that ray, you can't tell whether that ray comes from that actual surface here at an oblique angle, or if it comes from that projected area, which is then perpendicular to the ray. So in order to compute étendue of that ray, which is essentially its cross-section area times its solid angle, we need to take the projected area instead of the real area. So this would be a candidate for a building block. And it's a candidate because it's still not the real thing, but I'll come to that in a second. So here, it turns out that if we remove this projection thing from here, we recognize this is just area times cosine times omega, and we can be free where to attach the cosine. So what happens when we attach the cosine to the omega? What happens then geometrically is that we draw the tangent plane, the plane in which this area element lives. And instead of projecting the area, we now take the solid angle and project it down, and we get this entity down here, which is called projected solid angle, which by basic trigonometry is just the solid angle itself times the cosine. So if we multiply this together, we have a nice building block candidate for the étendue of that ray. It will turn out that this way of attaching the cosine to the solid angle is going to be very, very useful. So a projected small area element to a small solid angle element is the same étendue as from the small area element itself into the projected small solid angle element. But how about Snell's law? We all know Snell's law. Okay, this is the incoming ray. It's reflected into glass. It's closer to the surface normal. And many of us have learned Snell's law in school like that. And that's a way to write it, which I don't particularly like. I like it much better if I juggle the algebra a little bit. So I have n times sine is the same as n times sine on the other side, which already, it has the sweet smell of a conservation law, because obviously there is a quantity that remains conserved. So when I draw this in a little more close up, I have the ray coming in, the ray is reflected in, but instead of drawing the usual unit circle to draw these signs like over here, I now draw two different circles. One is in air with a radius of 1 or almost 1, and the other one is in glass, and the radius is defined to be the refractive index. So these two direction vectors are k vectors, which then have, by definition of those circles, the length of refractive index, look like that. But when I then do this sine-like projection, then we see that the length of this line would be the sine if that arrow has the length of 1. But if the arrow is longer by a factor of n, this is n times the sine. By definition of Snell's law, this is the same. So it turns out that this is a very nice geometric way of visualizing what Snell's law is doing to the light. So we need to somehow take that into account and redo our étendue building block with these ideas of using direction vectors with a length of refractive index. So when we go back to our previous image, then for the standard solid angle, this would be a length of 1. But now, if we again draw our parallel tangent plane and extend the length to whatever the refractive index is, where that area lives, then if I project that enlarged solid angle down, I get a quantity down here, which is the solid angle itself, projected down, which attaches a factor of cosine. And then because it has been growing linearly by n, and therefore an area by n square, there's a factor n square attached here. So our now real étendue building block, the étendue of this tiny light tube around that ray, is now area times n squared times cosine theta and the omega. Now, that's a mouthful to read, isn't it? This long formula. So what Henning and I found that it's really a good thing to take all that together and give it a name and a symbol and lump it together into something that we like to call infinitesimal angular extent dx instead of this long formula. So when dx is the index squared times the cosine of theta times the solid angle, where theta is the angle to the local surface normal, then the étendue of that light tube becomes simply dA times dx. So in the beginning, I said a good quantity must shorten. lengthy expressions, which is certainly something that X is doing, but it must also feature prominently in a law of nature. So is that happening? And of course it is, because otherwise I wouldn't be giving this talk. But let's see. So this is now refraction with an extended beam, not just a ray, but a ray bundle that is locally incident on some surface and then is reflected into the material. And with view of what happens with this single ray. So if this single ray is such that its projection down from the larger sphere is the same as from the smaller sphere when the ray is still coming from air, you see if such a oblique cone is coming in from air, then this is the solid angle of that incoming ray cone. When projected down, it is the angular extent of the light incident on that surface. After refractions, all the rays go into different directions. They are all closer to the surface normal because they have been refracted into the material. The solid angle is smaller. So in relation to the larger sphere, that is a smaller fraction than this one. But when I project that down, this green area down here, the angular extent, has precisely the same shape and location, because if things don't change for a single ray, then they don't change for this whole thing. So this green angular extent is not changing under refraction. Angular extent is conserved under refraction. And by the same logic, of course, it's conserved under reflection. So that's very nice. This is something that we like very much about our quantity, that it is participating in some conservation relation. So what's missing from this picture is free propagation. Let's look at free propagation quickly. So light is coming from this surface to this surface, and I want to know the étendue again of this light tube from here to here. So I project the angular extent down, which is then, the étendue from here to here is area times n squared times projected solid angle. I have an angle here, I have an angle here, I have a distance between here, and by some simple algebra, I know that this projected solid angle is this area, which looks smaller than it is by a factor of cosine. And it is then projected down by another factor of cosine, and it is projected to that sphere by a factor of 1 over distance squared, and then it's blown up by n squared. And all these complicated things are then just, subsumed in this tiny little dx formula, which is a good abbreviation. So this is a very nice simple expression for the étendue from here to here. And you can already see from the symmetry of these values that when I do it the other way around, when I want to know the étendue of the ray going from here to here, then with the same logic, this is the same expression. Étendue from here to here is just area times angular extent, and this is the same for both, which is just another name for étendue conservation under free propagation. So when we want to use this and compute the étendue of a complete ray bundle that goes from this extended surface to this extended surface, like all these rays, then the first thing to do is to split the screen into tiny infinitesimal rectangles. We pick one of them. We attach our tangent hemisphere, now with a radius of n, not 1. We take all the rays, making it to the next aperture. We zoom in, so we have a closer view. What we need to do is to project down to get that local angular extent, the angular extent of the ray bundle that goes through this point on the aperture to the next surface. And then this local angular extent will be similar but different for different locations on the surface. But here, the étendue of the light that leaves that little surface element to the next aperture is simply the angular extent times dA. And if I sum it up, étendue is the integral of angular extent over dA. And if you're familiar with the more complicated étendue integration formulas, this is really a great, nice simplification. And we now know that because it works for refraction and reflection and free propagation, it also works for gradient index, which is something I don't have the time to show here, but it's very nice. So we now have that this angular extent is really a nice quantity that shows up in étendue calculations everywhere. So that's about étendue, but what about radiometry? we send some light from here to here along this ray in this tiny little light tube. So light geometrically, no diffraction, going through this little square into this little square. And then we have Étendue from here to here is the same as here, is constant. But we also have energy conservation. So if light goes from here to here, from here through this surface in this direction, then the same amount of light, the same flux will arrive up here. So that is the same and remains constant. The flux remains the same. And if that's true, then the quotient of both will also have to remain the same. It is dividing the tiny amount of flux that goes from here to here by the tiny amount of Étendue that flux travels in. And that quantity, even if you may not recognize it directly from this formula, is what's well known in radiometry as radiance or photometrically weighted luminance. So what I'm saying is that the radiance or luminance of a ray remains constant for free propagation and along the same lines also for refraction and reflection. And if you don't believe it, then maybe you believe your eyes. So you see all kinds of things going on. You see magnification, demagnification, defocus, blur, all kinds of things. What you don't see is that the light that you see through the glass, through the optical system, which I'm holding in my hand, is changing the apparent brightness of what you see. And that is the radiance that you see. So radiance is constant along rays, which gives us the nice connection between angular extent and radiometry, meaning that here, if radiance as flux divided by Étendue is constant and an important quantity, then the flux is by that same definition obtained by integrating the radiance over Étendue. So we take each ray as little Étendue, we look how much light is traveling along that ray, which is measured by the radiance. We sum it all up, and then we obtain the total flux going from here to here. And our little dx, our angular extent, is again a nice prominent feature when we differentiate between the angular and the spatial aspects of it. And if we apply that to illuminance, flux per area, that's the definition of illuminance. I have a little area element somewhere, for example, on this desk here, and then light is coming from all directions, and illuminance measures how much light is incident here per surface. And illuminance doesn't care where that light is coming from. Of course, it's a function of location. Illuminance may vary from here to here. And if this is the differential definition of illuminance, flux per area, then the integral definition means that illuminance is the quantity that you have to integrate over whatever area to obtain the flux that is incident on that area. Some names, some physical units, and so on, that's all well known. So how is that now related to our angular extent? Turns out that if I have this situation, light is coming from the left, from air, and is refracted into some glass on the right, and of course here it's inside the TRR angle, then for all this formalism to be consistent, we must have a situation where the value, flux per area, if this is perfectly anti-reflective coded, must be the same on both sides of the interface. Because if all the light is refracted in, it must be the same amount, and it doesn't move sideways, so it's on the same area. So how does that happen? Does that work? And we see that flux is from the irradiance definition, the integral over flux per area over area. That's almost too tautological to express it. But from the radiance definition, we know that flux is also when we sum up our radiance for each ray over the Étendue of each of those rays. And if those two relations hold, and I have two different ways to compute the flux via integration, then the integrands must be the same. So this is now a relation that tells me how the illuminance or irradiance is related to the radiance of each individual ray. And of course, I can express my angular extent as n squared cosine theta d omega, or if I want to do it in spherical coordinates, it becomes even longer. It's all the same thing. But now we know that this irradiance is given as the integral over radiance over each contribution of angular extent. This nicely takes care of this question, is it consistent on both sides of the interface? because we have seen that the angular extent of each ray remains the same under refraction. Now, our expansion of this sphere and then projecting it down nicely took care of that. So by just applying the logic that we've been talking about, it's clear that this really gives us this consistent same value on both sides of the interface. So again, X qualifies nicely as something that abbreviates or shortens lengthy expressions, and also features prominently in an important relation, which is how the illuminance or irradiance is related to light from these incoming directions. There's also a nice connection to numerical aperture. Numerical aperture of a fiber, as you all know, if this is the limit angle of the acceptance of this optical fiber, then there is the numerical aperture of that fiber, which is defined in imaging optics as now not just the angle, but the sine of the angle multiplied by n. So here again, we have a relation between the sine and the trigonometric function and the refractive index, linear. And just like I can move from angle to numerical aperture, I can move from solid angle, which is what lives on the unit sphere, to my angular extent, which is similar but different. It's obtained not from the unit sphere, but from a hemisphere, which is blown up by a radius of n. And then it's projected down to give us what Henning and I would like to define as the angular extent. And when things are simple, when some things are constant, all these integrals just vanish and things become really very simple. So if, for example, for a spotlight, my target is an area and then the same telecentric cone everywhere, like a plus minus 30-degree cone, then that cone has an angular extent. The étendue of that light is the area of the aperture times that angular extent, which is the key formula to estimate, for example, what is a possible size of the LED, which I can use here. For telecentric cone, there is this very important formula, but again, angular extent just simplifies it. So that's one thing. And there's another interesting application where angular extent comes in nicely when things are simple. So when you want to look at the illuminance or irradiance on a sensor, which is very important quantity if you want to estimate noise, you want to see how brightly do you have to illuminate an object to get down to a noise level that you would like, then this is a screenshot from the optical design of a Cook triplet. When I apply these ideas here to see what is the irradiance here on this pixel on the sensor, I draw my hemisphere. This is probably going to be air, so this is a radius of 1. If I project the solid angle of that beam down to here, I have the angular extent of the light that's incident on that pixel over here. And then by definition, the irradiance, power per area on the pixel, is the radiance that I see when I'm, walking around on the sensor. When I look back, I of course see the complete aperture illuminated, and I see it illuminated with constant luminance or radiance because I'm looking at just one spot of a diffuse surface, if that is in focus. So that's constant. And because it's constant, I just multiply that constant radiance times the angular extent of that here to get the irradiance here on that sensor. Very simple formula. There's a more complicated one that takes into account the F number, but again, X simplifies that very much.
And here again, a little comment from my side. This is, of course, or in this case, of course, irradiance and the angular extent are both a function of the field coordinate. So as you can see in this image, the orange or the red cone has a different size than the blue cone. And so practically we would say the blue cone sees a different pupil than the paraxial red cone. And basically, we could go a step further and describe the cosine to the power of 4 effect in terms of the angular extent here. And by the way, the lens design is from the IODC 2014, if I remember right.
Yes, you do.
Yeah.
Of course, I wanted to something where I don't have to worry about copyright. And since I took part in that one, I know I could. It was fun, yeah. So thanks, Henning. This neatly solves a long discussion about relative illumination. what is the relative amount of irradiance that I get across a sensor? And this way of thinking about angular extent is the relative illumination, taking all the pupil aberrations nicely into account. So angular extent is everywhere in these calculations. So it does feature prominently in these Étendue and radiometry relations. We think that angular extent is a nice intuitive name. It's related to but different from solid angle. And it's also not used yet. So it's still something that we can choose. X is again an unused symbol, sounds like extent, gives all the right associations. And it does shorten expressions considerably. So that's why I think it would be a great idea to use angular extent in your thinking, in your writing, in your calculations, in your publications, in your presentations. And if at some point, maybe in August, I hear somebody talk about angular extent, I think that would be great. And with that, thank you for your attention. We can't hear you, Lynn. Lynn, you're muted.
Yes, sorry. Thank you, Julius, for the very nice presentation. You will certainly remember the importance of the angular extent. Indeed, very important if you want to consider the power on your sensor to make sure that you have a good signal over there as well. I received already a question of Lun. Lun, do you want to say your question yourself, or shall I read it? You can also unmute, so that makes it a little bit more personal than me just reading all your questions. So if you have a question, you can put it in the chat, or you can just raise your hand and you can ask a question yourself. Lun, please feel free to unmute. You don't have an unmute button. Aiken, can you solve that?
Yeah.
Can you hear me?
Can
you hear me?
Yeah,
Yes,
Lun, nice
yes.
to hear
Great.
you.
Sorry, I couldn't find the unmute button. First, congratulations. This is really exciting, and I have been struggling with, you know, sometimes it's just so important to name something, and the cosine direction cosine space integration of the phase space, it just has always been a hard concept to explain, and very thankful for the angular extent that you have named it. I just want to go to the free propagation page. If you can go to, I don't remember what page it would be, but it was one of the earlier slides. And as you go there, my question is,
this one or the next one?
No, it's titled free propagation. It has
free propagation. Yeah. Okay.
Yes.
Mm-hmm.
So when we are looking at each of the DA, the small area right there, thank you. And we're looking at each of the DA1 area, and we are observing that, of course, the ray from it can go to a particular small area DA2. And we're using that to calculate the angular extent in this case. But my question here is, if you consider this whole thing here, what really matters, just for simplicity, it's in the end for DA1, what matters for its angular extent is really just the boundary of A2, not DA2, but A2. So if you consider Stokes theorem, I don't know how to really explain it, but it's like, if you consider Stokes theorem, there is a surface integral to boundary integral mapping. So so the crucial information here, obviously, is just the boundary. You don't need to know any of the details in between, assuming everything in between obeys the direction cosine law. Right? So I think G.S. Derrick has a paper on this one, and he actually had a way of, he proved that mathematically there is a way of only doing the linear, boundary integral. So basically following the boundary using a line integral instead of a surface integral. So yeah, I just wonder if you have done some exploratory work on that to simplify the calculation of the angular extent.
No, I didn't do that. And I agree with you that applying Stokes theorem is something that is, you know, obviously on the list of possible things to do here. But there are, I think, two reasons why I haven't been following that path very much. And one is that whenever when a situation is as complicated as this one, then I don't do analytic computations. I just crank up my simulation software and I do a ray trace. And Henning and I have published a paper about how you tweak your light tools, Trace Pro, ZMax, whatever, such that it gives you the étendue of a ray bundle in also very complicated geometric situations. And maybe Henning is even going to talk about that in his talk right afterwards. So you know, when things are complicated, then these analytic solutions are becoming really difficult, and maybe just a numerical simulation, especially if it's easy to do, comes in handy. But there's another thing, which is that whereas Stokes' theorem is readily applicable if that is just when it's about étendue. If we do radiometric calculations, if I want to know, for example, what is the irradiance on that little patch here, if the light comes from here, then the distribution of radiance in that, you know, crooked cone is becoming important. And then I'm not sure whether it's so easy to apply Stokes' theorem here.
Absolutely agree. So yeah, if that surface there actually has different uneven
weights, essentially,
yes, that'll be a problem. But what I also wanted to comment on is even for computational burden in this case, or computational time, if you're doing a surface integral, that obviously is ON squared, and if you're doing a boundary, computational effort is only ON. I obviously have no experience of implementing this, and it will be, I mean, it will probably speed up the whole process. But anyway,
the computation will be much faster, but the time to set up the computation will be much longer.
That's true.
So in the end, I'm not sure. Okay, but thank you. It was nice hearing you again, Lund.
Thank you.
There is a second hand raised. So perhaps in view of time, I would propose that you put a question in the chat or in the Q&A, and that Julius answers in the Q&A. Is that okay?
Yes, that works for me. Yeah.
Okay,